Welcome back. Pretty quiet day. We've got clear skies once again here, so we're pointing that camera down instead of up. Let's take a look at the weather around the U.S. There's high pressure just about everywhere you look. The exception is up in the Pacific Northwest. If we pan up that way, you can see that very deep low pressure system off Victoria Island. That looks like it's down below 970 millibars, and it's got this very strong front moving northward through the Canadian prairies and the Dakotas. South of there, some very mild conditions in the western U.S., lots of 60s throughout that region, and they've got that deep southerly flow in place. Elsewhere around the country, looking out east, we've still got cold air advection working across New England, New York, and Pennsylvania. North winds all the way back to Chicago, all the way back to Memphis and New Orleans. So it's going to be another cold night for this entire area, but west of there, things are warming up. We're starting to get that return flow up from the Gulf. And there you can see that the dew points are not very high at this moment. The highest I'm seeing, 56 there at McAllen, but even in Houston, 29. So it's going to take a while to recover this air mass. And as we look further north, 20s across the Great Plains all the way up to Rapid City. Now, another way of sampling this air mass for moisture is looking at the precipitable water. And this is a summary of all of the available water vapor throughout the depth of the atmosphere. We can see that there's actually some very good moisture lurking just to the south. These purples indicate 1.5 inches of precipitable water and above. And we can see 1 inch sneaking up into the Rio Grande just west of Laredo. Up to the north, though, still dry. And I think a very good way to visualize this is with the skew-t. Let's do a skew-t for the hill country. You can see that area right there is definitely dry, showing about 1/4 inch of precipitable water. So the forecast skew-t sampling that air mass is going to look like that. Just a tiny bit of moisture up there, 30 to 35,000 feet, but below that, very dry. You can see that surface temperature, or that surface dew point of 26, tapering off to minus 30 to minus 40, up at about 7,000 to 8,000 feet. Then taking a look a little further south, let's sample this little wedge of air west of Laredo. This is just across the border in Mexico. And we can see, yeah, we're definitely picking up the moisture there. We go from 61 degree dew points, it trails off to about 50 up at 5,000 feet. And you can see these dew points are much, much higher than up in the San Antonio area. And then sampling the moisture further south. Let's go into this stuff here. That's going to be just east of Monterey, maybe a little further southeast. And there we can see the moisture, dew point 70. It tapers off, but it has considerable depth. Lots of moisture all the way up to 7,000 and a little bit more up above 10,000 feet. So those are some of the things you're going to look for when you're sampling the moisture return, especially in springtime when you're anticipating severe weather. Okay, one thing that has been in the news, of course, is Hurricane Iota. Let's take a look at that. Here's how the storm looked like last night at about 7 p.m. Eastern. At the time, it had max sustained winds, 160 miles per hour, 140 knots. That places it up in the Category 5 range. By 03Z, 10 p.m. Eastern, we shaved about 5 knots off of those speeds. And as it came inland at 9Z, about 3 a.m., it was 90 knots, gusting to 110, which is 105, gusting to 125 miles an hour. And then finally, at the very end of this loop, mid-morning, we were looking at 65 gusting to 80 knots. That was still in the hurricane range. And at that particular point, the storm was 110 miles inland. So I think we're looking at quite an extensive damage swath coming into northern Nicaragua. And then just bringing that current through the remainder of today. There's the loop, some fairly extensive remnants. You can still see the circulation there tracking along the Nicaragua-Honduras border. And I think we're looking at some tremendous landslide, flooding problems, and also a lot of damage inland where they're not really accustomed to these high wind fields. And the mid-afternoon conditions show that we've still got sustained winds of 55 knots. That's pretty much the high-end tropical storm category, almost hurricane strength. But we are looking for continued weakening as that heads pretty much for El Salvador. Checking in on our upper-level patterns. Got the jet stream pretty much running right through the middle of the North Pacific, coming on shore around Northern California, maybe a branch up towards Vancouver, and then we pick up another segment coming out of Canada down into the northeast U.S. So this pattern here is supporting a baroclinic high around the Great Lakes area into the Midwest, and we know from the surface chart that lines up pretty well there. This deep trough here off the Oregon coast with a downstream ridge, the jet stream segment in between, we know from our basic rules of thumb that we expect to find a baroclinic low right there, and that corresponds to that low that we saw near Vancouver Island. The troughing here may be associated with cold air advection, so I might be looking for a post-frontal cold air mass right around here. Do we see that? Well, I don't really have enough data there. However, provisionally I could stick in a cold front, maybe something like that. But really I need to see what's going on offshore. We can solve that to some extent by looking at the model charts. But we need to look offshore, and pivotal weather does not provide very good coverage out in the oceans. So it's a good idea to have alternates in mind. One is Tropical Tidbits. They've got a pretty good range of unusual places to select from. And I think this captures more of the system off the coast there. I can see that there is some cold air advection off the coast there. So yeah, I think maybe I could put a front along the coast, maybe right in that trough there. The warm front, that's definitely up to the north, so we're going to stick with what we have there on the surface analysis. And yeah, I think that matches up pretty good with the surface data. All right, so we're going to resume the dynamics lessons. I think a lot of people found that interesting. I'm probably going to cut the time down just a little bit, make it a little bit more bite-sized. Now, last week we covered the different kinds of fronts, thermal advection, stuff like that. We're going to talk about frontal intensity. Now you notice a few minutes ago I talked about frontal intensity on this Pacific Northwest system when I talked about it being kind of weak. Well, why do I think that? Well, if you look at these thickness lines, the red and the blue, they're spaced kind of far apart. Now, that doesn't take into account advection. The tighter the isobars are, the stronger the winds and the stronger the advection will be. That gives us a pretty simple rule. We can just form boxes between the thickness lines. Let me draw that out a little bit more. The thickness lines and the isobars. And you can see these form boxes. For example, there's a box right there. Now, the smaller these boxes are geometrically, the stronger the thermal advection. Now, I would say these boxes, they're kind of spread out. That's the reason I'm talking about that being weak, maybe moderate, but I would say weak. The thickness lines are spaced out, but there's some pretty strong advection coming through here. I'm sure it's a very windy day on the coast. But there is some stronger thermal advection up in this warm frontal zone. Look at that box right there. That's smaller than what we see off the Oregon coast. See, there's less geometric area in there. So the warm frontal advection, or I should say the warm advection, is stronger in this area right here. And I can kind of outline the area of strongest warm advection. That's going to be right in there. You can see in each of these zones you can form a pretty small-sized box. So this is all warm air advection. Let's see if we can take a look at a Europe. Maybe we can look at a front in that area. So here's England, here's Ireland, Spain, France. And out to the west we see a strong front. And if we draw the fronts out, I think we're going to see something like that there. You can see back behind the fronts, there's strong cold air advection. You can see those boxes are pretty tiny. So the cold air advection back behind this front is very strong. These measurements of thickness are a measure of the density contrast across the front. So a weak front is going to be characterized by a weak thickness gradient in that transition zone. The transition zone, of course, this area way back here. The front is always on the warm side of that transition zone. And a strong front is going to be characterized by a strong thickness gradient in that transition zone. So if the thickness lines are closely spaced, that's going to indicate a strong front. Now, forming the boxes, that indicates the strength of the cold air advection. But we don't really need advection to get a strong front. So the box method does not really indicate the strength of the front itself. It indicates the strength of the advection behind the front. And likewise, we can certainly use temperature to estimate the strength of a front. We don't really need thickness, but temperature gives us the measure at the surface or at whatever level we're sampling. So this is a forecast chart for the 23rd. We can see a very strong temperature discontinuity there in Texas. Let's zoom in on that. And there it is. We can use that transition zone and the strength of the contrast across that zone to determine how strong the front itself is. A weak front is going to be characterized by a weak temperature advection gradient in that transition zone. So the isotherms would be widely spaced. But in this example here, we've got a strong front, which is characterized by a strong thermal gradient and closely spaced isobars if we actually plotted that out. And it's not just the horizontal measures of temperature. We can also use the vertical measures of temperature gradient to assess how strong the front is. So let's go back in this transition zone. We'll go to about Waco and look at a forecast sounding. And what we look for is the lapse rate, the strength of the temperature change with that lapse rate. If the temperatures are falling weakly, that would indicate probably a weak front. But if the temperatures are isothermal in the transition zone or increasing with height, that indicates a strong front. In this case, we've got a very strong front right there. You can see it increasing from about 7 Celsius, that's about 43 Fahrenheit, all the way up to 12 Celsius, about 54 Fahrenheit, between 3 and 5,000 feet. So that's another measurement you can use, the vertical lapse rate within the transition zone, to determine whether you have a weak or strong front. This video is part of our continuing series on dynamics. If you want to jump in and see some of the earlier shows, there's the list, and that's also provided in the video description. And that's all I've got for this edition of Forecast Lab. Hope we'll see you back tomorrow for another installment. So have a good one. Take care. Bye-bye.